Good morning, everyone. So I was, were you asking me if we have a lab tomorrow? No.
Oh, no, I just saw the calendar.
No. But that was last week, right? So right now we're here, and so the plan for today is going to be to finish this chapter, and then we're going to have a review session. And if you have any questions, I'll answer that. So just to get a little bit organized. So remember that the most important thing happening this week is the exam on Thursday. Then we have you have a homework due today, right? So we're going to post a solution tomorrow so you can use it for the exam. And the laboratory is going to be due on Saturday. I gave you one more day, so in case you need that. But again, try to solve that. Even if you don't put a report together by Thursday, try to solve it and have all those figures and all those results done, because it's going to be an excellent training for the exam. And remember that, sometimes in the homework you're doing curve fitting with your computer, if you have to do that manually, it's very simple. You just trace a line through the middle of the points so you capture the main trend. For example, I already gave you the exams to practice with, so in case you have to solve problems related to finding strain parameters or a Young modulus, then you should bring a ruler. That's going to be very useful. But you trace a line, and I'm not going to ask you for a lot of precision about what is the slope of that line, the intercept of that line. As long as it's something that makes sense, I will give you full credit for that. All right, so unless you have any urgent question, I would say I propose I get started now, finishing this chapter, and then all the time that we have left, we use it to review some of the concepts and prepare for the exam. Okay? All right, so we are right here in this week, and we have covered all of this chapter except the 5 topics are left, or five. No, actually 4. So this was the last one that we saw, and summarizes all the possible failure modes in rocks. And something I forgot to say, and it's very important, is that notice that your Mohr circle may be somewhere in here. That would be your initial condition, and your Mohr circle is going to be bound by those lines. It means that you cannot go too much to the left because you go in tensile failure. That's what happens, for example, when you have hydraulic fracture. At the tip of your fracture, your Mohr circle is going to go to the left. You cannot go too high up because, or your Mohr circle cannot go too big because you're going to run into shear failure. That's what happens, for example, when you reactivate a fault or when you create failure around a wellbore. We're going to see that later on. Or you cannot go far to the right, and that's what happens when you lower the pore pressure so much that effective stresses are so high that you start to crash a rock. Your Mohr circle is going to be limited by those lines, and when you run into those lines, you're going to run into irrecoverable deformation and rock failure. And that's what we're going to explain a little bit more about in the topic that comes after, how we deal with those deformations after we go and we hit those lines. All right, the next topic in the list is very important, and it's about strength anisotropy. If you remember, we talked about stiffness anisotropy before. We said that a rock would be generally a lot stiffer in parallel direction than in vertical direction. Let me see if I find, I think I did a schematic about that right there. We said that, again, the rocks are going to be stiffer usually in the horizontal direction than in the vertical direction. because stiff layers are going to be deposited in horizontal direction and soft layers also in horizontal direction, and when you compress that, the solution is that you actually have higher stiffness in horizontal direction because you have to compress all the stiff layers. While if you do in vertical directions, you compress both with the same stress, the soft and the stiff. And the same way that we have elastic anisotropy or stiffness anisotropy, there is also strength anisotropy. Remember that stiffness is the slope of this curve, stress versus strain, and strength is going to be the maximum value of stress and strain. So what we usually see for strength is the opposite that what is seen for stiffness. They usually rocks in vertical direction will be stronger than rocks loaded in horizontal direction. Let me do a schematic of this because it might be a little bit difficult to picture if I just say it in words. Let me show you what I mean. So if you were to run a triaxial test where this is strain and this is stress, if you were to test a horizontal sample, it will look something like this. This is going to be a sample loaded in this direction, while if you were to test a vertical sample, would usually be softer, but is going to be stronger. And the reason for that is that usually bedding interfaces are weak planes. So this is a big assumption that I have here that happens in most rocks. And this happens for many rocks, and the reason is that sometimes the cementing between different types of minerals is not great. So the cementation with the same mineral is stronger than mineral to mineral. For example, you could have some rocks like unconventional rocks with layers of organic matter. Well, that organic matter may not be very well bonded to quartz or to calcite, and that's what makes those bedding interfaces to be weak. And there is going to be a case that is going to be actually the weakest, and that's going to be when these bedding interfaces are not horizontal or vertical. So vertical we saw is the strongest, but when the bedding interfaces are optimally oriented with respect to the load, this is the case which is going to be the weakest. Why? Because the interfaces are aligned with the plane in which I'm going to have the maximum shear stress to normal stress ratio. Do you remember that for the Moore circle, there is a characteristic angle at which we have failure, and it's not at 45 degrees, it is at a little bit more than 45 degrees. So usually when you have these bedding interfaces aligned at around 60 degrees, that's going to be the weakest point for the rock. And what all of this means is that the strength of the rock is going to depend on the direction in which you load it. And this is exactly what you see over here. What you see over here in this schematic is that depending on the angle in which you may have flaws or weak planes within the rock, your rock may be weaker or stronger. And it's going to be the weakest, this is that line, when those weakness planes are optimally aligned with respect to the shear failure line. If you were to load this rock with these interfaces perpendicular to the load, the load would not feel those interfaces, will not put any shear on those interfaces. And I have a nice example to show that, and it's this video over here. So in this case, what you're looking at, it's a sample of shale which is laminated. So you have some of these are layers, the white layers are rich in quartz, and the darker layers have quartz and also organic matter and clay. And what you see over here is that when these samples were loaded in axial direction, the fractures concentrated on those bedding interfaces. So let me tell you what you have here. On the left, you have both of those are X-ray images, but on the left, that's the outside, and on the right, you have two vertical cross sections, so you can see what's going on inside. And on the right, it's mine that already graduated did the interior to be transparent, so you can see the shape of the fracture in 3 dimensions in red. So in this one also you can see very clearly how these fractures would tend to concentrate on those bedding interfaces because they are usually weaker than going through the intact rock. And let me run this one a little bit more. So at the end, what we see that the final fracture is a connection between a fracture that goes through those interfaces and some that cut through the entire rock. If you were to load the rock perpendicularly, this is what you will see. So this one is a loading perpendicular to the bedding, and you can see, I'm going to try to stop it at the right place, that the fractures cut through the layers. And when the fractures have to cut to the layer, through the layers, generally it takes a higher stress in order to do that. That's why they are stronger. Let me finish this. And the last case would be the one in which the fracture is horizontal, where in this case just we have a single fracture going through all the layers. And here we have a case in which it's also loaded in axial direction, and some of the fractures, they go straight in between those lamination planes. I think the next one is a little bit better. Let me check. Yeah, so you can see also here some of those shear fractures that tend to concentrate in the laminations right there. This is a good one as they go through the sample. All right, so the only thing I want you to remember from this is that rocks are, remember, anisotropic. Real rocks are anisotropic, not only in stiffness but also on strength properties. And that's going to be very important, especially in shales when you have to consider drilling or hydraulic fracturing, because how the rock is going to fail is going to depend on the direction in which you load it. And this applies to shear, this is example, and also applies to tensile strength. And I have an example here that is going to require your input. Let me turn this on. All right, so what's going on? You don't see? Why you don't see the dog camera? Okay, let me try to fix that quickly. Okay, while I try to fix this, it might take a minute. Do you have any questions about the exam? Yeah.
Will the equation sheet be provided, like, can you post the equation sheet before the exam?
So if you take a look at the exams, they have the equation sheet right there. So at the end of the exam, you have the equation sheet. But what I'm thinking is to provide a new equation sheet. It's going to have the same equations, but it's just going to look a little bit nicer. But you're going to have the equation sheet there, so don't worry about that. Any other question? No, are you guys ready for the exam? So I know you have other exams the same day, so this is going to be short. Again, it's going to be based on the homework, on the laboratory. There is not going to be anything new, okay? What I am going to do, and I always try to do, is to have a new problem, which is not going to be the same as the one that you have in the exams. That's going to challenge a little bit yourself, and it's, to me, I try to make those problems so I see that you really understood the concepts rather than just repeated something from a previous problem. All right, okay. This is working now. All right, so I have a rock sample here, and it's a Berea sample. And the question is, do you think that I can split this rock just by pulling it with my bare hands? It's the same rock that you use in the laboratory. So I see many people say no, and I don't know why you guys have such a low confidence on my skills. But it may look as a silly example, but I think it's a very good one. So if I were to pull in this direction, I'm trying to pull now in this direction, but really I cannot break it. But look, I do this, I turn it, and I can open it very, very easily. So I can split this rock with my bare hands. It all depends on the direction. And what this simple example shows is also that tensile strength is also anisotropic, because I can pull the rock in this direction now with the fracture, and I'm not going to be able to pull it. But if I pull in this direction, it's going to be a lot easier. So for example, if you were to do, if you were to inject fluid in this fracture, and if you had the same stresses in this direction and in the perpendicular direction in this one, the fracture would tend to open a lot easier in this direction than in this direction, just because of the anisotropy of the strength properties. So in tension and in shear, And also in compression, rocks also tend to be anisotropic. We're not going to deal much with anisotropy in this class because it makes equations a lot more difficult, but remember that rocks are anisotropic, and eventually if you get to apply this in the future and if you get to work in geomechanics, you're going to have to consider that. All right, so let's go to the next topic now. And the next topic is about what happens after we get through the elastic limit. So let me come back. Over here. Okay, so as long as we're inside these three lines, the formations are going to be mostly elastic. But when we get to touch those lines, we cannot get outside. But when we get to touch those lines is when we're going to start to have significant irrecoverable strains. What that means is that when I get to that point, and that's going to be around here, if I continue loading, I'm going to have plastic strains that if I were to unload the rock, I'm going to have a permanent and non-recoverable deformation. So this transition is called, this is a transition from elastic deformations to plastic deformations, which are going to be permanent. We're not going to deal with the mathematics or the models about how to model this plastic part. We are just going to see what is that limit, and those are these equations that we have seen so far, like the limit for tensile strength or the limit for the shear failure. But we're going to see just this conceptually, okay? And about the homework that you have to do today, I took the work this morning and zeroed these deformations so they all start at zero. This is what I was telling you that I wanted you to do, just to make this zero, so the axial strain, the radial strain, and the volumetric strain, they all start at zero. And what you see in this test is that more or less around here I already have significant plastic strains. When I get to the peak, I have a lot of plastic strain. If I were to unload this sample, something that we did, but we're not showing the data in this experiment, the strain will come back very likely around this path, and that will be an irrecoverable deformation. Let me change. So if I were to unload this one, probably it would look something like this, where the difference between this and that will be all the deformation that you cannot recover, that was plastic. And why we cannot recover it? Because the rock has actually failed inside. Probably some bonds were broken or some grains were crushed, but it cannot be recovered. What is very important to know is that how that deformation takes place and how that failure takes place, it also depends on the level of confining stress or on the mean stress. If you have rocks loaded at a very low stress, like for example the ones that you did for the unconfined compression strength test, that was laboratory number 1, when you break them you saw very clear fractures and probably many of them. And that was the case with very low confinement, almost zero, no confinement at all. When you start increasing the level of confining pressure or to have more stress in all directions, your rock is going to start to fail differently. And I hope that you remember from your test for the triaxial test, especially if you did 300 or 500 psi, your fracture was a lot more defined than the one for the unconfined compression strength. And we didn't go to very high stress, but if you were to use a very high stress, your rock will start to fail quite differently, and the failure will be distributed all over the sample. And instead of having a very well-defined peak after which you lose all your stress, your rock will start failing more as a ductile material. And that's because now you have stresses acting in all directions, and your failure is not just a clear fracture, but it's distributed all around the rock. And I have one example here that shows a little bit better with actual data the strength. So here you have a rock sample, which is a marble, and it is loaded at different confining pressures, increasing from left to right. If you load it with almost no confinement, these are the fractures that you expect. Also similar to what you did in the laboratory, sometimes you have tensile fractures that are parallel to the loading. You start increasing the confining pressure, you have more defined shear fractures. You increase it even more and you have more shear fractures, and at the end you have a combination of compression and shear, and this is your result. And what you see on the plots of stress versus strain is that you go from something that has a very well-defined peak to something that tends to be ductile. And that's very important, because what this is telling you is confirming again that the higher the confining pressure, the stronger the rock is. But it's not only stronger, but also it fails differently. And a rock that, for example, you load under very high confining pressure, like here, it means that it's not breaking. You can take it to failure, but it's not that it's going to break catastrophically. It's just going to take a high load, but it's not going to break. It's not going to create a sudden fracture. And this is very important too, because what these curves are telling you is that here you're going from the surface, a fracture that you may expect on a building made out of marble without any confining pressure, to something that you would expect somewhere over here in the subsurface, where we do have an effective confining stress that makes a rock fail differently than what you would expect on surface. This is very important too, because we are going to see that when we get to talk about materials which are already broken, like this piece of rock over here that I took from the laboratory, this one is also going to have a shear strength, and that shear strength usually is going to be just a flat line, similar to what we have in these curves. Let me try again. It's just going to be like a flat line, like these ones, when we get to fault reactivation. And what that means is that that confining stress is providing that shear strength. If you don't have that confining stress, there is not going to be a shear strength. And you can conceptualize this into these three modes of failure, that when we load the rock and the stress goes down very quickly because the rock cannot support that load anymore, we call that a brittle fracture, and usually that results in a very well-defined fracture. When we get to a peak and it slowly goes down, we call that strain softening. When we get to the peak, but if we continue adding a strain, the material continues having that strength, we call that perfect plastic, and this was a case I was telling you for the faults. If we have a fault moving with respect to each other, it's going to be closer to this case of perfect plastic deformation. And on the other hand, if we have a material that, if we continue loading, it always gets stronger and stronger, that's called strain hardening, because it gets harder to break as you add more strain. In this case, by adding, by making fail the rock internally, you're making the pores smaller, and that's making the rock stronger. And again, as I was telling you, we're not going to deal with this problem mathematically. I would just like that you remember all these concepts. And I think we have one more topic to talk about. And this is just to think about a little bit again about failure. Failure processes are going to be quite different depending on the materials that we're dealing with. It's not the same to deal with the unconsolidated sand than to deal with the rock. The failure processes are going to be quite different. If you have an unconsolidated sand, like sand on a sand dune, like, and I'm going to come back to this, like this one, is going to fail quite different to a material that is more or less cemented, like a cemented sandstone, or a material which is more like a matrix of solid with pores inside, like this carbonate. At the end, it happens that we can all characterize all those materials with these three lines: tensile strength, shear failure, and compression. But the internal failure is going to be quite different. For an uncemented material, we're going to have that failure is going to happen through rolling of the grains with respect to each other, and sometimes even grain crashing. But on a very well cemented rock, we have more propagation of microfractures inside the rock. And in the case that we have fractures, there is a theory which is called linear elastic fracture mechanics that help us understand that a little bit better. And it tells us that we can have three types of fracture propagation. And this is going to be very important because we'll come back to this later in hydraulic fracturing. You can propagate the rock, a fracture in a rock or in any solid, if you pull from the sides of the fracture in direction perpendicular to the fracture. That's called opening mode or splitting mode. Let me make it a little bit bigger. This happens, for example, when you feel a fracture with a fluid and you start increasing the pressure, so the pressure exerts a stress on the walls of the fracture, and it makes the fracture propagate by opening. This is a typical case of a hydraulic fracture. But there are two other types that combine shear at the tip. And this is the mode 2, and these are the mode 2 and mode 3. The mode 2 is called in-plane shear or splitting. No, this is a mode 2. I remember one is tearing and the other one, I always forget that one. Sliding. This is sliding mode. So you have one side which is moving in the direction of the plane of the fracture and the other which is in the other direction. So what this causes is this fracture to propagate in shear, and this you usually end up in a fracture that will propagate this way. Not in the plane of the fracture, but in a direction with an angle with the fracture. And that's going to be the shear mode. And the other one is called mode 3 or tearing mode, in which the forces are applied on the plane of the fracture but perpendicular to the direction of propagation. And this is going to make a fracture also to propagate here at the tip of the fracture, but in shear. And these three modes happen when you break a rock and when you load it. Actually, for cemented rocks, like this one, many times, I don't think we're going to see it very well here, but I'll try. Pores cause concentration of stresses that, beginning at the pore, you can have some of those fractures to propagate. Also, you can see it, that one over there, and that's how the rock is going to fail in this type of cemented materials. So remember, it's not going to be the same depending on the rock type. And sometimes you may have even more complex rock materials that are not homogeneous but also have fractures inside. So that's going to change also how the rock breaks. Again, we'll come back to this later when we talk about hydraulic fracturing. I have a cool example to share with you about that one. And this just shows an example about how if you have a rock with already some microfractures, as you load it, those microfractures start to propagate till they make a big fracture, and that's how the rock fails. And probably that's the case of some of these materials in which we have smaller fractures, sometimes that we see or that we cannot see, or even it's not really fractures, but just, as we said before, planes of weakness that when loaded, they fracture, and fractures start to propagate until they coalesce into a big fracture that makes the rock fail completely. All right, I think this is everything. And again, the midterm is going to go up to this chapter, 1, 2, 3, and 4. So, do you have any questions about the homework due today? Did you guys try to solve the problem? Yeah? So the first one is relatively easy, right? Because you don't have any pore pressure. The second one, I'm showing you more or less what the solution is right here. And from here you need to get the Young modulus and the peak stress. Remember that this is a deviatoric stress, so you need to add the confining pressure in order to get the actual value of the maximum principal stress. And for the last one, now you have pore pressure, and this is going to be pretty similar to the case that you have right here, to this case, where all your data should more or less line up in one trend. If it doesn't line up, something wrong. Some points may be a little bit off, especially at a very high stress, but they should more or less line up. Once you get that, trace a line. Slope is that friction coefficient Q, and the intercept is the UCS. And then you can use the equations that I'm going to give you and then you have in the notes in order to convert that to friction angle and cohesive strength. What about previous homeworks? Do you have any question about that? Let me check. Do you have any questions about the exams? Did you have a chance to take a look at the exams? Okay, go ahead.
So one of the practice exams, I think it was the 2017.
Yeah.
There was one question about like how to tell, you were given like a log, and you had to tell if it was like a strike slip fault or a normal fault.
Okay. Which one? The 2019 or 2000, the fall or spring?
Fall 2019.
Fall 2019, okay. So let's open this, the first one. Okay, before I forget something, I don't remember for the fall or for the spring if it was a long or a short exam, but it's just going to be very similar to this, just 2 theoretical questions and 3 problems, okay? So this one,
Yes.
yeah,
It was
part C.
yes. How can you tell like if it's a strike slip fault or an angle?
Well, in real geological formations, at some places we can have the stress regimes that vary with depth. At some depth could be normal faulting, at some other depth could be strike slip, or it could be reverse faulting, because you may have stresses that change as a function of depth, and that's exactly what you see over here. So in this plot you have pore pressure, minimum horizontal stress in green, vertical stress in red, and total horizontal maximum stress in blue. So at depth C, which is this one right here, at that particular depth we see that the lowest stress is SH min, intermediate is SV, maximum is SH max, and that would be strike slip, right? However, look, at depth D, where we have this spike in stress, probably caused by a very stiff layer at that location. Now the minimum principal stress is the vertical stress, intermediate is minimum horizontal, the maximum is maximum horizontal. So in this particular at this particular depth, this one is reverse. So in this particular location, because of the presence of stiff layers that usually are rich in carbonates, the stress regime varies from strike slip to reverse. And we're going to see later on that that's very important for hydraulic fracturing, because that makes your fracture to go from vertical to horizontal, vertical to horizontal. Any other question? Yeah.
Can you show the homework, the most recent, like the one that's due?
Yeah.
Well, how do you tell if it's dilating or contracting again?
Um,
Dilating?
using this graph. The blue one is a volumetric strain. So let me write that in here. This is the volumetric strain. This is a positive variation. This is a negative variation. So when I have a change of strain that goes in this direction, that is positive. That's telling me that I have contraction. So if I could compare, you know, for that, I compared, let's say, this point over here and that point over there. So going from 4,000 psi to 8,000 diatoric stress, I know there was a contraction of the rock because it went to the right. However, if I compare, for example, these 2 points at 12,000 and let's say 13,000, there is almost no change in volumetric strain. Let me write that a little bit better. So the volumetric strain is about 0 because it is not changing. But when I go from 13,000, let's say, to 16,000 over here, I clearly see that now the change in volumetric strain is negative. And that is telling me that I have a dilation. Based on this plot, what I see is that at 16,000 psi of diatoric stress, the rock has the same volume as when I started. And that's because it got smaller, but then it got bigger as it went through failure because the fracture started to dilate. And the more you go to the left, the more dilation you have. Actually, in this particular case, we see that the rock probably got, these numbers are very small, but still they are meaningful. But the rock is about 4,000 bigger than when you started because of the process of failure. You're welcome. Any other question?
When we're zeroing this graph, are you saying to just take all the data and displace it so that the
Just to do,
initial item is
yeah.
0?
So what I'm doing here, I create another column and just subtract the first value. So I'm making my first value to be equal to 0.
And that's for all of them?
For all of them. Yeah. For example, if I were to pick another value over here, I'm always subtracting the first one. Same for this one, same for that one. So all your data is going to start now at 0. Okay, well, I'm checking my notes to see if I forget something. Let me know if you have any question. Yeah.
If a line intersects a circle and not just touches it as a tangent,
Yeah.
is that different? Like, is the intersection, does that mean something different from just being a tangent?
Well, I see. I see why you're asking that, but in practice, what happens is that when you do something like this, and your data does not exactly intercept the line of the straight line that you use, then when you get from here the value of cohesive strength and the value of the friction angle, the result is going to be that your Mohr circles are not going to exactly intercept that line. So with this line, now you're going to get also a straight line like that, and your Mohr circles, let's look, the red ones look pretty much on the line, so probably something like this, and like that, and let's say it doesn't intercept exactly, but I see the green one is falling short, so probably the green one is something like this. The first one, the second one might be overshooting the line, and the third one too. The fact that it's not intercepting the line or it's not being perfectly tangent, that means that the uncertainty that you have from this plot, you're putting it in here. So mathematically, it just means, that you are just moving the error from here to there. And physically, it means that your line is not so precise, or it doesn't capture all the data perfectly, but it's just a good approximation. And that's what we should think about these failure lines. They are just good approximations to the actual data. Even if you did your test which were perfect, exactly everything the same, the natural heterogeneity of the rock would also give some variability that all the data is not going to collapse exactly in one line, and because of that, your Moore circles also are not going to intercept exactly or be tangent exact to that line, just because of the heterogeneity of the rock. So don't worry if that line doesn't touch that line. Okay, I see something in my notes that probably I forgot here. If you were to do this 45-degree case, and if I were to plot this in this plot, probably will look something like this. This will be the case with bedding and weak planes at an angle. And one more important thing I'm forgetting here is that this transition from brittle to ductile, which is right here, it can be caused by stresses, but can also be caused by temperature. The higher the temperature, the more ductile rocks get, and also that coincides, the deeper you go, the more stress you have, the higher the temperature, and the more ductile the rocks get. And it also depends on time. Usually if you load the rock very quickly, it tends to behave more brittle than if you will load it over the term of millions of years. That's why we have rocks that are folded in geological formations that make an anticline, and the curvature can be quite high, but that curvature is there and it looks like a ductile deformation because it was bent over several millions of years. And because it was made so slow, it looked more like a ductile material than a brittle material. And there's one more thing here. Can you think about any other example that could make a rock more ductile? What about in shales, in unconventionals? Do you think about any factor that could make the rock more ductile? And I'm going to write this because it looks like I don't have it in my notes and I need to add it. So brittle to ductile transition is favored by increasing mean stress, or in the laboratory that translates to confining pressure, but it's actually the mean effective stress what you're increasing. It's favored by increasing the temperature. That's more or less obvious. Is favored by increasing the loading time, or which is the same, by decreasing the loading rate. And also in organic rocks, ductility increases as you increase the amount of total organic carbon. or kerogen, which is an organic polymeric substance that it's a lot more ductile than minerals. And not only that, but also the bigger the amount of clay, also the more ductile the rock is. And this is very important because in unconventionals, in organic rocks, you want to have a high amount of kerogen so that you have oil and gas in there, but you don't want that rock to be too ductile, because if it's too ductile, that usually leads to fractures which are just single plane, and they don't have the complexity that you have in a brittle rock. It's a lot better to have a brittle rock, because that would favor the propagation of fractures and more fracture complexity that eventually ends up in more surface area of the reservoir rock. You should imagine as a brittle fracture like when your phone, the screen of your phone shatters in 1,000 pieces. I don't know, ultimately I think the phones are pretty good. My phone, it didn't crash the screen, even I dropped it several times. I think in the last 2 years it's fine. But before that, I remember every time my phone will fall, the screen will shatter immediately. Well, that is an example of a brittle fracture. A ductile fracture will be mostly just one single fracture that, again, will not have as much branching as what you may want for hydraulic fracturing. And there is a rule which applies to some rocks, but not to all, and just be careful about this. But there is work that says that the bigger the ratio of the Young modulus over the Poisson ratio, the bigger the brittleness. So let me write it here. This is just valid for some shales. And what this summarize is that the stiffer your rock, usually the more brittle it's going to be, and the smaller the Poisson ratio, also the more brittle it is going to be. Usually carbonates have a low Poisson ratio, so if you have a lot of carbonate, your entire rock probably is going to have a low Poisson ratio, and that's going to make it more brittle. And I think that's everything I have in my notes. So again, do you have any specific question? Yes, Ms. Jacoby.
Spring 1A midterm?
Where?
The spring midterm?
Spring midterm. Let's go there. Spring.
Yeah, spring 1A.
Ooh, this one?
Number 3, about, this is about the multiple choice for number 3.
Okay.
Can you explain like how to eliminate or select those answers?
Okay, yes. So the question here is, which of these apply to rock shear strength? It could be 1, it could be 4, it could be 0, okay? So the first one says rock shear strength depends on the direction of loading with respect to the rock bedding and lamination. What would you say to that, guys? This would be true, right? So you would circle that. And because this is what we just have seen right here, that depending on the direction of loading with respect to bedding, your strength, your maximum peak stress is going to be quite different. Let's go to the next one. Next one says the shear strength of uncemented sands is always 0. That is, uncemented sands cannot bear any stresses. And that's false. That's not true. Because we know that uncemented sands do not have any strength when they are not confined. But when they are confined, when you have an effective stress on it in another direction, they actually can be quite strong. Number 3 says rock shear strength is independent of the friction angle. And that's not true, because we know, and we have seen this here before, that the bigger the friction angle, here the steeper this line is going to be, and the steeper this line is, the stronger the rock is going to be. So you need 2 parameters for strength, the intercept and the slope. The bigger the intercept, the stronger the rock. The bigger the slope, the stronger the rock too. Yeah.
So between phi, theta, and beta, which one is the friction, which one's the fracture, and which one?
So I follow the convention that phi is the friction angle. I used beta a couple of times to refer to the angle between the plane in which you apply the maximum stress and the plane of failure. That's beta. The one that, let me see if it's right here. This one will be beta, right there. And let me see if I have it in another figure over here. No, I don't have it here, but this angle will be beta. And theta, I didn't use theta. When did I use theta? In my notes?
Can't remember.
Let me check. So there is beta. That's beta. And I don't think I used.
Maybe that was a typo of mine.
Okay.
So
Would
beta then is the fracture angle. Could be defined as the fracture angle between
beta?
the plane of stress and the fracture.
Yes. Yeah. Okay. And let's continue with this.
What's the difference between UCS and SO again? The cohesion of
Say again?
what's the difference between UCS and S not?
Those two are intercepts of these equations, of this equation and that equation. And they tell you physically, that's what they are mathematically, just intercepts of those equations. Those equations are equivalent, but they are just written in different spaces, different variables. And physically, this means the maximum stress that you can apply on a rock when the other stress perpendicular to it is equal to 0. And this one physically, S0 means the it would be it's a sort of a cohesive strength, or it's the maximum shear stress that you can have on a plane when the normal stress is equal to 0. So this would characterize more or less the shear strength of your rock when you have no normal stress. So when normal stress is equal to 0, then this is what you get.
And the unconfined stress is when there's when there is normal stress?
When there is no stress in the perpendicular direction to the loading. But you shouldn't think too much about a physical meaning about this cohesive strength. It's just an intercept value that tells you how cemented the rock is. That when is equal to 0, it's not cemented. If it's different than 0, that means it's cemented.
Okay.
Yeah.
So shear strength depends on all those sums, right?
Yes. Depends on all these parameters. Okay, and let me finish with this one. Shear strength is independent of friction angle, and no. Shear strength failure criterion depends on pore pressure, And I will say to that no, because that's actually the last exercise in here that we see that it doesn't really matter what the pore pressure is. Rocks just care about effective stress, and effective stress already account for that pore pressure. All right, so let me check over here. There is no pore pressure in the failure criterion, just effective stresses. You guys know how to solve this, right? This is basically an example of numerical integration using the trapezoidal rule. So you start with the density here of 1, then you have the rock, relatively light, then denser and denser. So here, in order to get to the depth of 2000, then you need to add these 4 intervals. This one, that one, this one, and this one. Here you have an example about computing a Young modulus. So remember that you need to know how to compute an axial strain. If you have a force, this is exactly what you have in the lab, how to compute the deviatoric stress or stress. You have the length of the sample, diameter of the sample, and here you just have to plot that and then fit a line to that and measure a Young modulus. And for this case, just draw a Mohr circle for that. And I think in this case, you just have 2 problems. Yeah, 2 problems. And let's check. The other one is very similar. It was just with different numbers for the spring. Let's check the one for the fall. Okay, so here the objective of this problem was to emphasize that your vertical stress just depends on true vertical depth, not on measured depth. So I remember that in this problem some students computed the vertical stress by adding all these lengths, this length, this curvature, and plus that length. So no, that's not what you should do. What you should do is just to compute the true vertical depth from the surface to this point, and that's what is going to give you the total vertical stress. This problem, I like this problem a lot because we haven't seen this yet, but conceptually you should know what this is. You have total stresses, you have pore pressure, and then looking at those values, you can tell what is the stress regime. Also, this will be an inverse problem to what you did. In most of the problems I gave you, you had the density and you had to compute the vertical stress. Well, in this case, you have the vertical stress variation with depth. You have to compute the gradient, which is the opposite to what you have been doing before. But if you understand the problem, you will have no problem in order to do this. And I like this question too. So do you think the tectonic strains are 0 in this case? No, why not?
The horizontal stresses aren't equal.
Because that's one point. The horizontal stresses are not equal. And the second point is that horizontal stresses are higher than vertical stresses. And that only happens when you have the tectonic strain. If you have a passive tectonic environment, your stresses should be more or less the same and should be lower than the vertical stress. And also, this is another example of the inverse of what you have been doing so far. So now, instead of asking you to construct a plot of strain versus stress I give you the plot of stress versus strain, and then you have to figure out from there what happened with this experiment. And just to make sure this, I remember that in this exam some people were calling things differently, but just to be clear, this type of loading, we will say it's parallel to bedding, or here you have a parallel Young modulus, for this case of 90 degrees. Why? Because the load in this case is applied in direction parallel to the layers. So this will be parallel, 0 will be perpendicular because the load is applied perpendicular to the bedding, and of course this is 45 degrees. So remember, the blue, if you get the blue one, that will be a parallel Young modulus, parallel to bedding. The red would be a vertical Young modulus. And in this particular example, we see that some of the rocks loaded parallel to bedding are actually stronger than perpendicular to bedding. That sometimes happens when the bedding interfaces are actually stronger than the matrix of the rock itself. And I think that's it. That's it for this test. So you will see that in all the tests you have an equation sheet that, again, I'm going to try to put, if I have time, into something that will look a little bit nicer, that you can also keep for the second midterm and for the final exam. Okay? Just one more thing, guys. With all this thing about this coronavirus, the university is thinking about what to do in the future if this gets worse. If you have some international travel, then probably it's a good idea that the later, especially if you go to the affected areas, right? The risk areas right now, that you stay at home for a few days. I'll accommodate all of that. Don't worry. And they're saying there's even a chance that we might have like some weeks that we may have to cancel the lectures too. But I think that's not going to be a problem. We'll follow up remotely. We'll see what happens after spring break. I think for now, everything is okay, but later things might change. But again, if after spring break you come back with a cold or anything, that you don't feel comfortable about, then just let me know. I'll accommodate all of that. All right? I'll see you on Thursday. Please arrive on time. Okay?